What do you see here? Is this a horse or a donkey? To your surprise, it's a mule, a similar animal like horse and donkey. And it is hybridized progeny of female horse and a male donkey. Similarly, Liger's offspring of female tiger and male lion are formed by interspecific hybridization. Now, the question arises, what is hybridization? Hybridization refers to the mingling of genes or features to create a new hybrid or modified species. In chemistry, hybridization is a process of mixing and overlapping atomic orbitals to create hybrid orbitals with the same energy. Pauling first introduced hybridization as a concept. Hybridization plays a crucial role in explaining the geometrical form of polyatomic molecules like methane, ammonia, water. Now, let's discuss some of the characteristics of hybridization. First, the number of atomic orbitals and the number of hybrid orbitals that are created are equal. Second, the energy and the shape of hybridized orbitals are constant. Third, in comparison to atomic orbitals, hybrid orbitals produces bonds that are more stable. Now, let's be familiar with the conditions for hybridization. First, the orbitals in the atom's outermost shell are hybridized. Second, the energies of the atomic orbitals that combine to generate hybrid orbitals should be equivalent. Then, for hybridization to occur, the electrons do not necessarily need to be excited or elevated to higher energy level. And it is not necessary that only half-filled orbitals participate in hybridization. In some cases, even the filled orbitals of valence shell take part in hybridization. There are various types of hybridization involving s, p and d orbitals. In this session, we will discuss the hybridization involving s and p orbitals. We will start with sp hybridization. Here, one s and one p orbital overlap to create two sp hybrid orbitals. Such a molecule in which the central atom is sp hybridized are linked directly to other central atoms possess linear geometry. For example, in the case of beryllium chloride, the ground state electronic configuration of beryllium is 1s2, 2s2. In the excited state, one of the 2s electron of beryllium is promoted to vacant 2p orbital. Here, one 2s and one 2p orbital get hybridized to form two sp hybrid orbitals. Each of these orbitals overlap axially with a chlorine 2p orbital to form two sigma bonds with a linear shape and 180-degree bond angle. In case of sp2 hybridization, 1s and 2p atomic orbitals are mixed together to create three identical sp2 hybrid orbitals. For example, in BCl3 molecule, the ground state electronic configuration of central atom boron is 1s2, 2s2, 2p1. In the excited state, one of the 2s electron is promoted to vacant 2p orbital. These three orbitals, one 2s and two 2p hybrid, to form three sp2 hybrid orbitals. The three hybrid orbitals so formed are oriented in a trigonal planar arrangement with the overlap with 2p orbitals of chlorine to form three BCl bonds. Therefore, in BCl3, the geometry is trigonal planar with a bond angle of 120 degree. Moving forward to the third type of hybridization, that is sp3. Here, 1s and 3p orbitals combine together to form four hybridized sp3 orbitals. Let us take example of methane. Here, the central atom is the carbon atom, having 2 unpaired electrons in p orbitals in the ground state. In the excited state, one of the 2s electrons is promoted to the p orbital. Thus, 1 2s and 3 2p orbitals form 4 sp3 hybrid orbitals. All sp3 hybrid orbitals forms a sigma bond and are directed towards the 4 corners of the tetrahedron with a bond angle of 109.5 degree with a tetrahedral geometry. Now, we know that a molecule with sp3 hybridization is tetrahedral in shape, but the shape of ammonia with sp3 hybridization is trigonal pyramidal with bond angle of 107 degree. Let's discuss the reason behind it. In ammonia molecule, nitrogen has one lone pair and repulsion between lone pair and bond pair is more than the repulsion between bond pair and bond pair. Due to this, the molecule gets distorted and the bond angle is reduced to 107 degree with trigonal pyramidal shape. Similarly, oxygen atom in water molecule possesses 2 lone pair of electrons. Because of this, the oxygen molecule experiences 2 types of repulsion. One between lone pair and a bond pair, and the other between a lone pair and a lone pair. The bonding angle of water molecule is reduced to 104.5 degrees due to additional repulsion, giving it a V shape or a angular geometry. We have come to an end of this session. Now, can you try to predict the hybridization compound containing double and triple bonds? Well, we will discuss in the next session. Now, let's summarize what we have learned.
Manorama Horizon. Learning made simple.